Thanks a lot. So to put the context, so far I think we've seen a lot of work in automation, especially when you deal with IP addresses or threat intel, which is anything but malware itself. So you have domain names, IP address, email, and whatever else, you can clean up a lot. But when it comes to actual malware content, you end up sending hashes to each other. And if you got to analyze, now you are into the game of going to VirusTotal, going sandboxes, and whatnot to extract information. What I'm going to be presenting here is things we have done. We have service available to extract, in this case, Yara rules automatically to automate a whole sequence of steps that you otherwise do manually. So about myself first, I have 2 hats, and that's why I have no hair. I'm a professor of computer science at UL, University of Louisiana at Lafayette, which is about 6 or 8 hours from here. And I also have a startup, Cythereal. Some people call it Cy the Real, and in that case, I'm the real Cy. We're based in Lafayette, Louisiana, and New Orleans. We have 2 locations there. We are still, in a sense, stealth mode, if you can call stealth mode there, but we're very early stage. I also have a hat, which is just a change of topic here. I'm also an editor-in-chief of a journal, Digital Threats Research and Practice. The research and practice is actually bridging both the research and what we're seeing here in terms of practice. We have special issues that our first special issue that's coming out is from the FIRST conference. First issue is from FIRST, the 2 different FIRST. But it's a practitioner, so we have actually taken work that's done in FIRST and then gone through some process to publishing it. So some of the work that I've seen here would make for good articles for this journal. One of the intent is to take knowledge from the field and bring it to research sites. So it's the other way around, okay? So if you'd like to talk about it with me, I'm available to discuss how we could bring your ideas to a published forum. That's the big picture of what I have. So typically, IOCs, as in indicators and indicators of compromise, you take some indicator you got, and the next step is, how do I get bigger set? How do I expand the net? So you have a little piece, and then you want to extend the related sort of indicators. So typically you go from indicators to some notion of campaign. You say, hey, this indicator appears to be APT 28 or something. And then from there you say, okay, what all do I know about APT 28? And you expand the set. So that's the usual thing that you want to do, whether it's incident response or threat research or threat hunting or stuff. You start with the indicator, you want to expand the set. The place I am focused on is when you have an indicator, then it connects to malware, and then what? So typically when you have malware, you get some more indicator, and then more malware, and more indicator, and more malware. And you might do this story on VirusTotal, for example. So you get indicator, you find the graph link, and then you keep traversing the graph link. What we are saying is you have an indicator. At some point, we get the malware. From there, we extract Yara rules automatically based on code. It's a shared code. Extract Yara rules. We also identify campaign, and the intent is with the Yara rule, we can find all of those related malware that you're trying to go through by cycling through IOCs. We connect them all, and it's automated and so on. So that's the big picture I want to share with you. All right, so let's go back here. So this is at least the use case we have. You have something suspect. First thing you want to do is separate. Is it false? Is it true? If it's false alarm, you leave it alone. And if it is valid, then you got to figure out more about it, and then eventually get some IOCs, TTPs that you can use for automation. And so current model, the way I see it, at least, is when it comes to malware, that's my major focus, is you have these three things you can do. You can look up reputation, you go to VirusTotal, hybrid analysis, whatever. If you have a hash, you go look up reputation, and then from reputation, you could either get indicators from the reputation, or you go to a sandbox, whatever sandbox of your choice, and from there you get indicators. Or if you get nothing else, you go to these threat exchanges. You go on your Slack feeds or whichever community you have. From there you cycle, and you go through this cycling process to answer the questions you want to answer in there. So, and then when it comes to determining, okay, I think it is bad and I want to get some more information, if you have to go deeper in it, then you go through Ghidra and any kind of disassembly, and this is more like a threat level, deeper stuff. You extract TTPs, nodes, and so on. What we want to do is something like this. This is our vision, or what we're presenting is, especially when it comes to malware. You upload the malware, you download Yara, and then you go do what you need to do with the Yara hunt. And so this is our full picture of pipeline, the way it works. Let me show. You get a malware, we find. So our core strength is similar malware based on code similarity. We find similar malware. And so once you have the similar malware, we also extract Yara from similarity. And then, of course, you can search various repositories with the Yara, so it extends. So you start from my repository, and I have maybe 6-7 million samples, and they have probably several 100 million samples. So you go search them, and you get more Yaras, and then you can have, with those malware, you have the associated IPs and domain, and that's your thing that you can now use for connect back to the thing that you know how to deal with, which is IP addresses and so on. Here's a little thing we did. It's a very quick study just to see the power of it. I think this is cyber, if you guys are familiar, CNMF, CYBERCOM's US Cyber Command, they published malware, and so we took some samples, and these are 8 samples that put some time. We put it in our system. We did some grouping. There are really 8 samples, so really 4 groups. And then we found that one of the group, when you did Yara, the similarity match, one group related to this thing called external. It's a malware. From my point of view, I don't really go read malware myself. I just put it in the machine and let it do its job and find the name and say, that's all I know. So I'm not personally into getting into disassembly and debugging, all of that stuff. I could do it, but I don't like doing that. So here, the next piece I found was group connected to something called LoJack. There's another was XAgent and EXE. So this is just from matching. And when we took some of these hashes and searched online, we found that it connects to one of the hash was used, one of the old hash that we found was used in attack on TV5 Monday. So this is just the path. So I get a sample, I get the Yara, I find matches, and I find, hey, this is connected to a previous attack. And another sample we found was attack connected to Italian military, 2018. And this whole process, eventually say, hey, this is APD 28. So this whole process of going through, it took about 30 minutes. That's whole path. And now it's going to be a little bit faster than this was. We did about 7-8 months ago. So processes were a little slower. Now you could probably do it in 15-20 minutes. Now, this is a case we are now working on, which is sort of a predictive defense, but I'm going to tell you what I mean here, this slide. So you have current model of protection is you have some asset you want to protect, and you have a bunch of things at the protection level. Protection level is your antiviruses, web filter, and whatever else you have to keep threat out. These are protection filters. And then you have detection filters. Detection filters are your EDR. Assume you already been breached, and now do I detect this? So you have 2 sets of filters. When I use the word filter here, it's like generic. It could be a machine learning-based filter. It could be rules. It could be whatever. You might have layers of them. And then you have Usually they are driven by threat intel. You're getting some intelligence from outside and you're feeding into your filter and you're somehow guiding these filters. The issue here is how do you decide what threat intel comes into your environment? So right now, if you're going to get a threat intel feed, you get a subscription, and now you are drinking from a fire hose. You get a whole bunch of stuff, and you can say, oh, no, not that much. I need a little bit less. So you set up filters by saying name. Okay, if you see some particular name, you give it to me. Or you set up Yara rules. You construct Yara rules. And so what we do in this case is, this is the part where we want to be automated. The intent is we look at the protection filters, things that have been blocked by your antivirus, by web filter, by whatever mechanism that blocks malicious contents. I'm not trying to worry about SSH connection or other stuff. So if your malicious content being delivered, it's been blocked. So once you have that blocked, we analyze it and now give it to the threat side, say, hey, I want to know these things, because these are the things that are attacking me today. So it's not just that, hey, this is attack happening around the world, and I need to worry about it. Say, these are the things that are attacking me today. And here the thing is, the things that are attacking you today may be variants of things that are attacking somewhere else, but they may not match their variants. They may not, the same Yara rules coming from somewhere else may not apply to you. So we go here, we extract the Yara rules, feed it in the filter, and so that's sort of automate that process of looking at who is attacking you today, extract the rules, give it to the threat intel side, threat research side, and then get the IOCs to stay ahead. Yeah. And this also addresses some of the issue of when you get this threat intel, is it already stale? So by the time you get the IP addresses, domain names, it might be more than 24 hours, so some of the lifetime is much shorter than that. So this addresses the issue of trying to get something which is current. Now, here's a little, I got to explain to you what this diagram. So, but what we're trying to do is, our intent is to fill the gap. So there's a gap between what the protection, your protection environment and the attack surface. There's all kinds of attack happening. Not everything can be blocked by you. And so what can be blocked in the attacks that are there, there's a little gap. And what we want to see is, can we fill that gap? So this little thing we have done, we are currently working with Deutsche, I don't know how to pronounce that name. I'm still trying to get it right. Okay, I'll rather call it German. So German Telecom, we're working with them. And I have to explain what this gap means here. So what we did was took a trick bot Yara that we generated. So, and we put it on VirusTotal. And we're getting from VirusTotal new samples that are coming in. And for each of the new sample, we know the detection as of that day. So this is 0-day detection. 0 day as in 0 day on VirusTotal. When it was received on VirusTotal on that day, what was the detection? So we're picking up that detection. And then we are looking at all of the data that is coming from that trick bot sample. In this case, there were 109 samples over 3 or 4 days. So very, very recent current sample, 109 of them. And we're looking at all of the 109, and we look at 70 or so antiviruses and look at what were they able to detect or not detect. All right? So this says, and the missed is the gap. What did they miss? So this one here says there are 2 antiviruses that did not miss any. So the miss rate was 0. The gap there is 0. So if you use the Yara rules, they're not adding any more value because in that case, they missed. Here, if you go, about 30 or so missed 1 sample. So that means if there are 109 of those trick bot variants ended up in your network, 1 would have gone through. Likely if you had any of these antiviruses. Now this is where interesting part happens, is about half of them, or slightly less than half of them, had a huge miss. So when you go to the other end, there were several antiviruses that missed over 100. All right? So that's the gap. If any of these 109 variants ended up in a network and you had that particular antivirus defending you, you would have a chance of being hit. Okay, so that's the gap. So what we are looking at is, can I fill the gap? Fill the gap by predicting. So I'm saying, hey, these are the samples that are coming in. Let me generate Yara for the specific kinds of stuff that show up on my network. Generate a Yara rule. So if these variants go further away, then I am able to catch them. All right? So this is, we did it about 2 or 3 weeks ago in terms of demonstrating that there's a value here of what we can fill. Now this, I have to qualify here. What we find is that how various AVs antiviruses behave change a little bit based on the actual particular malware family. So for TrickBot, maybe someone performed very poor, and you pick up another one, and that someone may perform better in this. So there's no necessary consistency that if you just pick on this side of the curve, you're just happy and say, okay, my probabilities are reduced. It's just that it may shift over time, and it may shift over particular family. So there's gap that we can try to fill. So that's the big picture, all right? So now I'm going to see if my demo works. I'm going to show you. And if I don't get to connect to the network and all, I have slides, visuals to show you there. All right. So I have little screens that I'm going to walk you through. In this case, this is our, the top part is not a whole lot in this data I'm going to show here. So these are samples that are coming in on a daily basis, and we have on the left the upload time and so on. Okay? And so what we do is we look at this. I'm going to point you to some specific columns that are of interest before we go. So I'm going to show you the global matches. So the global matches there. The global matches column shows the number of samples in my collection. Mine is, I consider global, where I have a match. So if my 6-7 million samples I have, I take this thing and match based on a very high threshold, like 0.7. So we have a similarity 0 to 1, 0.7 match. So at that level, we see that this one sample has no match, and there's a 2, 16, 10, 412, and so on. And there'll be some that have a pretty high matches. So you might have, for example, 1,707. So if you're doing threat research and you go to VirusTotal, you have to do these analysis, some of it. We do it right away yourself. Now the second thing you'll see is this thing called evasiveness. So, and this is a little bit late there. I mean, we are not keeping it current every day at this time, but essentially what it shows is, if I look at this column, evasiveness, it shows, I'm going to tell you what this 0.789 means. It says that, and it's related to 15/71. On that day when this is the VirusTotal detection ratio. So if you see a sample on your network, you see, hey, how is this sample, how are other AVs dealing with it? And you say this is 15/71 we're able to detect, and the scan age is 40 days. So 40 days ago when we tried, that's the time, that's when 40 days ago, 15 out of 71 AVs were able to detect this one on VirusTotal. And so this data and some other information we use to construct what we call as evasiveness. Evasiveness is what is the chance that this can actually pass through some arbitrary random sort of AV system. So we're not saying any particular, but given a profile of AV systems, what's the chance it can pass through? So 0.789, while percentage is not the right way, it's 78.78% chance it might pass through. And then this column 1, he says, hey, can we generate Yara rules? In this case, we are able to generate a Yara rule. So typically what will happen is you say, okay, I think this is of interest to me. You go there, and you might say, here are the samples that it matched. So this is actually showing the matched samples. Now, I would have shown you the actual what we do is match. So it just so happens that yesterday we did some update, and it's broken the similarity, all right? Now, as about half an hour ago, I was told it's fixed. So I'm going to click on it. If it doesn't work, just be aware that's what happens. So here, this is not a threat analyst. I don't expect researchers to do it, but this part I'm going to show what we do under the hood. So I don't expect people to go click around and look at this, right? My expectation is everything is automated, but this part is just for you to get confidence. Hey, this is what it's doing. So here, this says that we have this particular malware, and we are doing a search. So this is the result of searching them. And the result of the pack, the original sample, when you match, there's a match with 0.7055 similarity. And now here, this is what you typically will do with if you were actually doing reversing, you will use bin diff and whatnot to find similarity. It's going to take a little time to load up the similarity, but I'm going to shift attention here and see if I have one already loaded. So this is one which I have already loaded, comparison. It's finding comparison is basing it on code. So if you look at any piece of code here, let's say I do a code. This is code, similarity. See, this code is based on similar code, although some of the values are changing, say 18610, 10808. Some of those values are changing, but it's based on code. So we match polymorphic. Even if you have polymorphic changes and other changes, we match them. So it's a very, very versatile in terms of the kind of matches it can do. So all of the register renaming, the classic things that are done to defeat AVs, we do that. So this part, we don't really look at it. This is just under the hood. Then what you do is you construct the Yara rules. I mean, I'm going to have to show you a Yara rule, maybe. A second. This is not there. All right, so let me. All right, I'm going to create the Yara rule. So typically you just go, you automatically create the rules, and this could be done over API. You upload a file and say, okay, make a Yara for that. And it's going to construct the Yara rule here. It's going to come back with the Yara rule. And then you take the Yara rule and you go search on hybrid analysis or something like that, and I'll show you. So this is your Yara rule here. So this is based on shared code. So since we are matching at the code level, we construct, and then it deals with polymorphism. You see all of these question marks and so on there in terms of identifying where the variations would be. We have next version coming maybe in a month or so. It's going to be much more mind-blowing in terms of the ability. But so we have much more. It's like, I think it's very, very cool. Now you take these Yara rules, of course, and now I have some searches that I've done in hybrid analysis. Let me show you this. So in hybrid analysis, this is the Yara rule, one of the rules that I've taken, searched here, and you find samples. This is I just did today. It matched the sample. So this particular malware we picked up some time back, and we're matching it with this particular various matches. You have all of this. So if you wanted hashes that are relevant, these are your hashes. If you want IP addresses, domains, and so on that's relevant, you could go, let's see, login, and let's see what I get. So here's your domains, IPs associated with the malware. Okay, so you took the malware, got the Yara, do the search, you have all the IPs and domain. That's the whole path, okay? So, of course, that's it's back to my presentation here. Pretty much I've just told you what we do. Now it's only a matter of detail now. If I'm going to show you some interesting code here. This is a part of how, when we are talking about similarity, I want to make sure this is really, I like this one because, so here's some piece of code that you don't need to understand the code. I'm going to just put similar code next to it, and you say, hey, these two piece segments of code are similar. They're both doing string obfuscation. So what they're doing is they're constructing string on the fly. So there's on the left and the right, they're different strings, but they're all four length string. You'll see 4 green letters. There's a 6F, 706F, 656E. Those are ASCII codes. On the other side, there are 4 ASCII codes. And the 0, for example, this if you are really into reverse engineering, so this is 0. This is the last. If you're terminating the string, you put a 0. Here, there is no 0. But you see this XOR EAX. That's putting 0. Different ways you can construct zeros. We automatically find that these are similar. Next version, we're going to generate Yara for that. That's what for the first version, Yara is when there's not as much expansion of code. Next version will be mind-blowing in terms of Yara we get there. Okay? And so in terms of, again, I've talked about most of it. That's it. So the key is, again, and what I want to emphasize is this is automated. While I have shown you interactively, you can upload files. Wait, the next version we'll have a feedback loop. Right now, you upload file, you sort of twiddle around, you wait, and say, hey, did you have the result? And you come back. Next version, we will have a pushback where once you have finished it, we give a feedback. You give us a URL, we ping back saying, okay, work is finished. Now go ahead with the next step. And you pick up the Yara and you do whatever else you need to do from that. Okay? So my expectation is this automation here. So you pick up, this is the front side, remember the prevention filters. These are prevention filters. You pick up anything that is hitting you today. You feed it into the system here. We generate all of the information by automatically correlating and whatnot. And I've only given you one slice of it. We generate threat alerts. So we also have a mechanism to check, hey, it looks like you have a lot of attempt by, let's say, Emotet as an example. We are seeing these kind of threats. They have been stopped, but we have seen those threats. We're going to analyze that, give an alert. If we see alerts, threats that have high evasiveness, hey, I think it's something to worry about. So we're still tuning up. We don't want to add more alerts to that you're already getting. So we're trying to tune up. So we have, for example, we create rules for APTs and say, hey, if we find something that matches APT, I need to let you know, look, there's a match here. So we generate alerts. And the idea is the next step is we give you the Yara that you can use to construct IOCs that you can then feed into IDS, EDR, whatever else. So create the loop from prevention to threat intel, back to EDR. Okay? That's it. Questions? Yeah, just a second. If you have questions, if you have a question, I have some goodies for you. All right.
We'll do questions while the next speaker is getting set up.
So with your technology, does it currently only handle PE executables, or is it also able to handle like MSIL or like say like maybe like a compiled auto IT or something like that?
Anything that can be assembled by IDA.
Oh, IDA, okay. Okay, all right, cool.
Alrighty. Anything else? Oh, yeah. How do you ensure you're not doing false positives? Is that the?
Yeah, so that's good. False positives is a killer, right? You got false positives can be a killer. So what we have is, so at the bottom of it, we have a huge database of common procedures. Anything we find, all right? We have a huge database of it. That's the core. When we are creating signatures, every byte sequence you see is a function. And now the determination is this function that we are picking up, could it appear in a benign code, right? So this is where the machine learning revisited comes in. So what we do is we have statistical information of these large collections. Anything that occurs very often. Like if the frequency of occurrence is high, we can safely assume that it's likely occurring across a lot of malware, therefore it could occur in benign. We also have benign data in our collection. So whenever we identify things are benign and anything that matches benign, we say this is likely to be benign, so we're not going to do that. So we go aggressive in terms of ruling out. If it just minorly touches the benign, it's okay, this is benign, let's throw it out. So so we also take advantage of IDA's flirt. So if IDA is able to give it a name, we say, okay, this is benign, let's leave it alone. So the IDA flirt, populating our own benign collection, or if VirusTotal says this is benign, we say, okay, that's benign. Okay? So we err on the side of caution. Okay? So there may be things that occur very few times, and they're occurring in benign, but we could possibly use it, but sorry, not leave it alone.
Thank you very much.